Hello everyone, I am Dr. Sirajul Faizi. Today in this video, I am going to talk about heterocyclic compound for 4th semester students. So let us start learning of heterocyclic compounds. So let us start with the nomenclature. You can see here oxygen, sulfur or nitrogens. This is hetero atom and always getting first positions. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Now you have the common name nomenclature system, Hans-Widman nomenclature and replacement name. So focus on this nomenclature so that you can apply this in every heterocyclic compound. So focus on these three examples. Look at here: oxirane, oxirane, thiirane and aziridine. So aziridine. So you can see the nomenclature with the help of Hans-Widman nomenclature. Now, common name ethylene oxide, ethylene sulfide, ethylene imine. Now, replacement name. You know this is the cyclopropane. So, oxacyclopropane. This is also cyclopropane. So, thiacyclopropane due to sulfur and azacyclopropane. Now you understand replacement nomenclature. The base is cyclopropane, aza is there, so aza, thia and oxacyclopropane. In the same way, this is not the, it is a very easy task you can do yourself. Dioxyrenes, oxaziridines and diaziridines. Now again, this is very important questions from where you can start. For both oxygen, you have the choice, go to the 1 and 2, here 1, 2, 2. But here you have no choice. Give the positions 1 to oxygen and 2 to nitrogens. Here also, if you have 2 NH, then you can go numbering, you can do numbering from anywhere. Now the important things here you can look at, this is oxirene, this is thiirene. Now again here 1H azirine and 2 azirine, 2 nomenclature is there. 1 due to position of hydrogens and here you can see 2. So 2H azirine and 1 azirine. Like 3H diazirines and this is in equilibrium with the diazomethane. So I hope this part will clear. Now same you can try the nomenclature of 4-member ring, dioxetane, thietane, azitidine according to Hans-Widman name who already learned in the first class. Now again trimethylene oxide, trimethylene sulfide and trimethylene imine, radiofunctional name. And then replacement, you know, cyclobutane, so oxacyclo, thiacyclo and azacyclobutane. Practice it with these examples: oxide in thiet and 1 azitidine, 2 azitine, azet, and practice it with this. Now friends, you have the 3 compound to study like benzofuran, benzothiazine and pyrrole. So again nomenclature start from this oxygen and this is the benzene and this is the furan. Now this bond position is B. So this ring and this ring attach with this positions which is B. So this is benzo and this is furan. So benzofuran, also known as coumaron. Now, if you change the position of oxygens, then what will happen? This is A, this is B. Now it becomes the C. So benzo C-furan, isocoumaron, and this is out of syllabus. First, your knowledge, you just give the nomenclature. But this two compound is important for you. Now friends, how you will synthesize this coumaron? So starting with this aldehyde alcohol, which is salicylaldehyde, you have acetic anhydride, Perkin synthesis, carbon-carbon bond formations, and then you can see this after rearrangements you will get such type of compounds. This is the your coumarin. Then again it will go with the brominations. You will get the 1,2 bromo here, and this is the position of 3,4. So 3,4 dibromocoumarin. Then KBr H2O in place of basic medium, you will get this, and after heating you will get this, after decarboxylation you will get this. So this is one synthetic method of benzofuran. Now again, starting from orthophenyl hydroxylamine, you have the keto groups here. You will get this type of compound, orthophenyloxime, and then this is unstable showing, again you will get this. So finally you will get the disubstituted benzofurans. And according to Fischer-Indol synthesis, if you start from here, so you can, if you change this nitrogen with the oxygens or oxygen with the nitrogens, then you will get the substituted indol, benzopyrrole. Now again you can see the first position on sulfur. So this bond is B. So thiophenolphthalein or benzo B-thiophene. This nomenclature is different. This one is different. Again change the position of sulfur. Now how you will synthesize this ring? Starting with the mercaptocinamic acid using this type of reagents. Again cyclization. After cyclization, deprotonation, you will get this ring. This is the preparations. Now my friends, chemical properties of benzothiophene. So nitration, you can see this is 1, 2, 3rd positions, main product and side product. The aromatic system say preferred here. So carbon 2 attack and carbon 3 attack. This is 1, 2, 3. This is 2 carbon or this is 3 carbon. If this Y plus, you know this is the electrophile attack here, then this is the 2 form. If it is attached here, then this is the 2 form. Now what will happen here? These two, why this one is preferred over this? The aromatic system is say preferred. Aromaticity is same here. An aromatic system is decomposed, so disadvantage. Again you can see. So position 3 is favorable in case of nitration. So just give the logical why C3 is more preferred than C2. Now my friend, pyrrole derivative with condensed ring system, because 1H indol, benzo D-pyrrole. Same as you can see this hydrogen, if will go here, then 3H indol, benzo B-pyrrole. Indolenine, it is common name indolenine. Again you can see N-methyl isoindol. So check this type, this is not in your syllabus, again for knowledge, but focus on these two structures. So how you will prepare the indol or benzopyrrole? Starting from this compound, there is a formations of nitrogen carbon double bond, which is known as ship base. After zinc reaction you will get this product, and after decarboxylation you will get this. This is and another mechanism. So again, fission indole synthesis is very important for indole, so you can check it, practice it, write it down. You can see this is the mechanism of fission indole synthesis. Okay, write it down several times, how this bond is breaking here, making carbon-carbon bond. What is this? This is 3,3 sigma tropic rearrangement. You already learned about the pericyclic reactions. Now you can see the cyclizations. So practice it this one. Now important here, chemical properties. If electrophile goes here, beta positions mainly, halogenation, nitration, sulfonation, alkylation and acylations. And other reactions, if you have, you can see with this aldehyde group attached here, this reaction is very important, and here you can see. So this is the chemical property. If you have Grignard reagents, then this hydrogen transfer with the magnesium iodide, and then if you have this, so substitution occur here, substitution occur here, substitutions. In the sodium, you can see sodium, again substitution occurs there, this position. So the pyrrole reactions, this is only indoles and benzopyroles. So write it down and practice it several times. Now again, this is 1, 2, 3. So here you have to clear the alpha and beta meaning. This is the 2 position is alpha and 3 position is beta. So if you have NHO sulfur, indoles, coumaron and thiocoumaron. So this is the beta preferred, I already seen, alpha sometimes and beta alpha. So you can see if you have this type of, so alkylation, acylation, sulfonations, like this goes attack. So after heating rearrangements, so alkylations, beta position means 3 position, acylation beta, but sulfonation alpha position, it is 2 position. Now coumarons, you can see we have, this is the advantageous here, and this structure is disadvantageous. This is the resonating form. So when electrophile attack here, means at 3 positions, and when electrophile attack here in case of, this is a benzopyrrole, benzothiazole. So there is this 2 resonating structure, and another if electrophile attack here. So what will have a non-aromatic disadvantages, and here you can see the aromatic advantages. That's right, that is the 3 is more preferred than 2. Now my friends, go to the 2 heteroatoms. The oxazole, 1, 2 oxazoles, oxazoles, 1, 3 oxazoles, isothiazole, which is not in your syllabus, but thiazole, 1, 3 thiazole, pyrazoles, 1, 2 diazoles, and imidazole, 1, 3 diazoles. So look at here, how you will prepare the isoxazole and its derivative. So not go to the derivative, first you focus on preparations of isoxazole, because you have less time. By 1,3 dipolar cycloaddition, it takes place by 4n+2. This cycloaddition reaction. In scale 1 superficial reaction, 1,3 dipolar cycloaddition is one step through a cyclic transition step. You can see this is the triple bond, here triple bond, this is dipolar natures, 1,3 dipolars. So after heating you will get this products. So 1,3 dipolar, one of the component nitrile oxide is dipolar. You can see this is dipolar. Dipolar means what? Here is the positive and negative dipolar. So charge atom carbon oxygen in 1,3 positions. So this is also in mesomers, this structure and this structure. Now friends, you can see the starting from these compounds, then cyclization occurs. You see carbon, nitrogen, oxygen bond formation, then minus H2O, this H and this formation of double bond. Then break. If it is coming from here, so if react with hydroxylamine, you will get this one, and again cyclization occurs, you will get this product, and this is your target product. Now chemical properties, you can see it is sensitive to bases resulting in ring opening. If you can see this, if react with the base, you can see this is also in your study, in your syllabus, to how to synthesize this. And if you have base, and then you are getting this product by electrophilic reaction, you are getting here. So basic strength in aqueous solution. For objective questions, this is very important. Go to the imidazole, more basic than thiazoles, parazole, hexazole. How you will know that? Because pKa value here. Now check the proton here, proton here, proton here, here no protons. So pKa value for the conjugate acid of the bases. Now oxazoles, you know the oxazoles, again starting from here, how you are making this carbon atom with 1, 2, 3 oxidation level, and then you are getting this ring, and this is your products. Again, if you are starting from here, you will get this. So again, you can see how you will synthesize oxazolene rings by this pathway and this pathway. So more generally, if you have such type of compound, then cyclization occurs. This is nitrogen and oxygens, and R1, R2, if you have this condition, this is the reaction scheme. You can change the R1, R2, and you will get the tri-substituted products. Here again, if you are breaking this disconnection, then you are getting this product. So it is difficult to alkylate the amide nitrogen. Reactions run similarly in both pair, so it is easy to acylate the primary amide nitrogen. So this one will not change. This one is more favorable than this. Now difference in saturation of the product can be reached by selection of the proper oxidation level of the starting compound. Now you see 6 pi electron, the non-bonding electron pair of oxygen, takes part in the function of aromatic sextate. Now here you can see these positions and these two positions. This is due to alkene here due to carbon nitrogen bond, this one, and one due to carbon oxygen bond, here carbon nitrogen ship base, here carbon oxygen. So look at here 1/5, 1/5, and this is the 3. And this 3, this one. So how you will synthesize the ring? Starting with these two compounds, you are getting this. Starting from these two compounds, you are getting this. Again, you can change this oxygen with ammonia, and this is the your reaction scheme. Write it down. We will discuss and in class also. Chemical properties, you can see you have here 5th, 4th, like this. So one of the most stable derivative of 2-oxazolene is 2-methyl-oxazolene, and this compound has an interesting feature. Okay, so see how it is opening different products. Now thiazole, same way, this is the 6 pi electron system. Now Hansch synthesis, how you will synthesize this ring. This is another methods, this is another methods, another method. So form synthesis of this ring, write it down. We will discuss each reactions in the class. Now chemical properties, you see electrophile, position you can check, electrophile, then position you can check. So this is the reactions, pyridine like properties. Again, how this reaction is propagating. Oxidations, thiazole ring is resistant to oxidations. Now how you will synthesize the pyrazoles. This is the pyrazoles. Direct synthesis, oxygen change with the NH, then this is the pyrazoles. So acid-base properties of pyrazoles is also very important. How this is forming hydrogen bond, this hydrogen forming with the other tartameric forms, Wertfeld tartamic and atrial tartamerism. So write it down in your notebook. This is the reaction scheme. You can see the advantage, not advantage, not advantage. Why it is by substitution on the carbon 4. This position is also important. So NH position always get 1, then 2, 3, 4. So substitution on carbon 4, bromination, nitration and sulfonation. You can see nitrations. This is the 4th position in pyrazoles. So my friends, I hope this video will be helpful to you. We will meet tomorrow class. So before coming class, you should write it down in your notebook so that we will discuss. Thank you.